Welcome to the spring semester, Organic Chemistry 2, and we'll be starting at Chapter 12. But please bear in mind that Organic Chemistry is a cumulative course, so I emphasize, all that we have done in Organic Chemistry 1, you need to go back and refresh your memory of that, because we will be building on that foundation in this second semester of Organic Chemistry. So we'll start our discussion in Chapter 12. And the reactions that we'll be looking at in reaction type that we'll be looking at is elimination reactions. Okay, so in this presentation, we'll be looking at elimination reaction and in specific, a specific type mechanism called the E2. And then we'll look at some specific reactions, we'll look at the mechanisms, and we'll look at a particular one that's called the Hofmann elimination. Okay, so let's begin our lecture. So elimination reaction, as the name suggests, it's the elimination or the removal of atoms or groups of atoms from a compound, typically saturated, to form an unsaturated functional group, typically an alkene. So we have seen this type reaction when we looked at the general type reactions of organic chemistry. So let's review. So here we have a organic reactant, and this time it's a chloride. In the presence of a base, notice KOH, heat, and a solvent. Typically the solvent is an alcohol. This set of conditions will give elimination, and as you can see here, we have Cl and H. Those are the groups that's being eliminated to form the unsaturated double bond right here. I should point out that it's possible to have the elimination at this position, but you will quickly see that putting the double bond here is the same molecule as putting the double bond here. So it's only one product that's possible from this elimination reaction. This, of course, is called the dehydrohalogenation. Hydrohalogenation. And of course, D means the removal. The second reaction that we look at here is the dehydration. D, taking off, hydration, water. So here we have an alcohol, OH, and here we have a hydrogen. So if we have dehydration, the reaction conditions here will be an acidic medium in the presence of heat. Notice heat is generally used for elimination reaction. So the elimination of water, here's the water as a product, and taking this off will put the double bond here. Same thing here. If we had a hydrogen over here, well, there are hydrogens here, but if the elimination occurred here, that would be the same molecule. So once again, for elimination, what we have is the removal of atoms. And notice the two atoms that are removed, or the atoms that are removed, are from adjacent carbons. 1, 2. Not from the same carbon. Here we go again. One carbon, second carbon. So it's on the adjacent carbon, and that's why we form a double bond here. Let us look at the mechanism in a little more details here. So the elimination occurs whenever we have a good leaving group, a potential leaving group, and that's key. So X here is coming off with its electrons, X minus, to form a leaving group. You may recall from last semester, a good leaving group is a very stable base. It's a weak base, such as Cl minus, Br minus. In other words, its conjugate acid is pretty strong. So we can tell that we have a good leaving group. We need a good leaving group for elimination. As the name applies, elimination, to get it off, it has to have the potential to leave. And those that have the best potential of leaving are leaving groups that are weak bases. Also, we have a hydrogen on the adjacent carbon. Notice it's a potential proton because these electrons here will swing in and this will leave with its electrons. So that's why we have H+. So now you can see why these reactions require a base, because it's going to pull off this hydrogen as a proton, leaving these electrons here, which will form the double bond. So that's the mechanism. Notice that this mechanism occurs in one step. There are no intermediates, no carbocations, no radicals, no intermediate, one step. So that's called a synchronous reaction, no intermediates. Okay, so let's look at the mechanism in a little more detail here. We say it's a bimolecular reaction. Why bimolecular? Because in the important step, and this is just one step reaction, it has one reactant and two reactants here. So two reactants, bimolecular, are required in the most important step, which is the only step of that reaction. Of course, as you know, if it's the only step of that reaction, it goes through a transition state and then onto product. So here's your base, pulling off the proton. These electrons come in, and this leaves as your leaving group. So we have our base here as BH plus, base H plus, because it has taken off the proton. When we do a more specific reaction, we'll see what that base actually is. But the bottom line is we are forming here as product an unsaturated product, an alkene, by elimination. So once again, this is a bimolecular, or an E2 for elimination, bimolecular. Why bimolecular? Because two reactants are used in the important step and only step of this reaction. So if we look at this in terms of the reaction profile, the energy, so we start off with our reactants, two reactants. It goes through a transition state, and by the way, you should know what the transition state really means, and onto products. Okay, so let's apply what we have just learned. So we have examples of elimination reaction. Now we're going to use a base, KOH, a specific base here. So here's the base. So K plus and OH minus. Here is our molecule, right here. And what I want you to do is to look at that molecule carefully and make some observations. The first observation is it has a chlorine, which means it's a good leaving group. Why is it a good leaving group? Because after it has left, taking its bonding electrons, it's a conjugate base, Cl minus, and that's pretty stable. A base will pull off a hydrogen as a proton, and notice this hydrogen is on the second carbon or the adjacent carbon from the leaving group. There are no hydrogens here, so this is the only product that will form. That's the only product forming the double bond right here. So again, as we emphasized last semester, you will have to carry out careful observations of your molecules so that you can apply the concepts that's being discussed. Let's look at this molecule here. Here's bromine. Of course, looking at your periodic table, you can see that the bromide anion is a very good leaving group. So in the product over here, you would not expect to have bromine as part of the organic molecule. And here it is as a leaving group because it has left. The reactant is a base. Here's a hydrogen. The hydrogen is on the carbon that's adjacent to the leaving group. In some books, you'll see this as a beta elimination or a 1,2 elimination because it occurs from the adjacent carbons. So in the presence of a base, this base will pull off this hydrogen, these electrons will swing in, and that will leave, giving us our double bond right here, and bromide as the leaving group, and of course, since we have OH as the base, we have water as the product. So again, you should be able to look at an organic molecule, determine if it has a good leaving group, look at the reaction conditions, and be able to predict the elimination product. Let's take it a step further. I mentioned that the elimination in an E2, that the leaving group and the hydrogen must be trans to each other, right across from each other. Let me see if I can go back and show you. So as we did here, we had here the hydrogen and the leaving group. They are trans. It's a trans arrangement. So here's another requirement for the E2 reaction. The leaving group and the hydrogen must be trans to each other. With that said, let us go here and see if we can apply that concept. So here is a molecule. Here is a chlorine. That's our leaving group. And on the adjacent carbon is a hydrogen. But it also has an adjacent carbon over here, which has a hydrogen. So therefore, in the presence of a base and heat, we'll have elimination, but now we'll have elimination from the trans arrangement of the hydrogen and the chlorine. So therefore, here's a chlorine and here's a hydrogen. That's a trans arrangement. So therefore, the double bond will go right here. Notice over here though, this hydrogen and this chlorine are cis to each other. So this product here will not form by an E2 mechanism. Why? Because an E2 mechanism requires the hydrogen and the leaving group to be trans to each other. So look out for that. Let us take it a step further. And now let us look at predicting the major product. So in this molecule here, here's a carbon that has the bromine. Here is a carbon that has a hydrogen. Here is a carbon that now has two hydrogens. So as you can see, KOH, heat, will give elimination. KOH is a strong base. And Br is a good leaving group. By the way, this should be Br. And Br is a good leaving group. So what happens here is KOH will take off this hydrogen as a proton. These electrons swing in, and this leaves to give Br. Let me correct this. I'll correct it on the PowerPoints which I gave to you. So this would be this double bond here. It's possible for the KOH to take off this hydrogen to create a double bond here. So we have two possible products. The question now is, which is the major product? Let's see if we can determine that. Okay, let's look at this molecule, or hypothetical molecule. We have a carbon that has two alkyl groups, and we have a carbon that has a leaving group, and it's adjacent to another carbon that has three hydrogens. Okay, so if we have a base that's pretty small, because this carbon here has the hydrogen, but it has very bulky groups bonded around this hydrogen, this base will abstract this hydrogen here to put the double bond here as a major product. Why is that the major product? Because that's the highly substituted product. So small base will abstract the hydrogen from the carbon that's most crowded to give the most stable alkene, called the Zaitsev product. If, on the other hand, we use a very bulky base, and I'll give you an example of a bulky base in a second, that bulky base cannot gain access to this hydrogen because of these bulky groups. So it pulls off a hydrogen that is accessible. And as you can tell, these hydrogens here are not crowded because hydrogens are pretty small. So this bulky base will pull off one of these hydrogens here to give this alkene as the major product. Notice that this alkene here is not the most substituted alkene. You'll see in the book that's referred to as the Hofmann product. So the major product of a reaction depends on the size of the base that's used. Let's apply that concept. So here we have two types of bases. One here is the bulky base, strong bulky base. It's called LDA, lithium diisopropyl amide. This is isopropyl group, diisopropyl, and it's an amide because it's a salt and a lithium, LDA. So if you write LDA as chemists, we will understand that you mean lithium diisopropyl amide. Another bulky base, as you can imagine, is potassium tert butoxide. You may recall from Organic 1 that tert butanol is a weak acid. So if you can pull off that hydrogen that's bonded to the oxygen to create a salt, it's a conjugate base. Since it's coming from a weak acid, it's a strong conjugate base. So these are two examples of strong conjugate bases, strong bases that are bulky. Examples of small bases here, of course, as you can imagine, sodium hydroxide or potassium methoxide or even potassium ethoxide. The ethoxide here is pretty small compared to these. So we have two types of bases that we can use here. You just have to pick one to determine what the major product that's needed. So let's apply this. So if we have this molecule here, CH3, bromine on this carbon as the leaving group, CH3, CH, H, and CH3. So notice here that this carbon here has the leaving group, and the adjacent carbon is the one with the hydrogen. So if we use here a small base, it will take off this hydrogen here to form this transition state and give this as the major product, which is the most highly substituted double bond. As you can imagine, it can also pull off this hydrogen over here, and it will. And what we have here is this transition state to give this as the product, but in this case it is the minor product. That's the minor product. We have some names for that, as you'll see in the book. That's the Hoffman product, and this is the Zaitsev product. Let's see if we use a bulky base. So if we use a bulky base such as LDA, remember that's very bulky. It has the choice of pulling off this hydrogen here that's adjacent to the carbon that has the leaving group to form this alkene. But notice that this hydrogen here has a methyl group bonded to the carbon that has that hydrogen. So that hydrogen is a bit crowded. So that's why it is the minor product. This hydrogen, on the other hand, has a carbon that has two hydrogens, less crowded. So therefore LDA, being a bulky base, would prefer to take off this hydrogen as a proton. These electrons go in, that is the leaving group, to give this as the major product. So again, you'll have to exercise observation here and a strategy to make the product that you really want, depending on your choice of base. So let us apply this here. So if we had this molecule as a starting material, here's a leaving group, here's a carbon. It has here hydrogens, hydrogens, and hydrogens, because this is an adjacent carbon. So we can form a double bond here, we can form a double bond here, or we can form a double bond here. Of course, forming a double bond here and here results in the same molecule. So if we use a small base such as KOH, and please, whenever you write these on the quiz, make sure you clearly identify the base of choice. So this would give here this product, which is, as we said, the Zaitsev product, or the more substituted alkene, using a small base. Using a bulky base, it would not take off these hydrogens here, but one of these, because it's less crowded. So the double bond would go right here, where this chlorine would go and the double bond would form here. So again, make sure you do the observation and make sure you determine what you need and use the appropriate base. Okay, let's see if we have another example here of applying this. So if you're asked to predict the major product for these two reactions. Again, as you know, organic chemistry, you'll have to exercise your observation skills and your application skills using the concepts. So the basic observation here is this molecule has a bromine, very good leaving group. The reaction conditions here, KOH, base, but a small base. Heat, more than likely elimination. Same molecule, leaving group, but in this case it's LDA, bulky base, heat, elimination. So what you'll have to do is look at this carbon that has the leaving group. Notice we have three possible carbons bonded to that carbon that have hydrogens. So it's possible to form a double bond here, here, or here. Since the base is small, more than likely it will form the more stable alkene, pulling the hydrogen from the more crowded carbon adjacent to the leaving group. LDA, being a bulky base, it would pull off the hydrogen as a proton from the carbon that's least crowded, which would be this. So you may want to pause the video here and write your product on a piece of paper and then click to see what we have as the answer. So here we go. This would be the answers. KOH, small base, double bond goes here. Granted, if you put the double bond here, same molecule. However, this is only one arrangement here where LDA, bulky base, proton leaves from here because CH3 is right here and would form the double bond right here, and here it is. So again, for the first reaction, the base is small, which will give the Zaitsev product. And for the second reaction, the base is bulky, which will give the Hoffman product. So again, get familiar with those names because as you will see on these questions, we tend to communicate using these terms and these names. Okay, let us see if we can apply this even more. Show how to carry out the following transformation. So we have this molecule, and we're trying to get this molecule as the product. What reagents and steps of reactions would we put here to carry that out? As you can see, you will have to resort to reactions from last semester. That's why I emphasize, don't forget the reactions that we did last semester, because of course, as I said earlier, this course is a cumulative course. It relies heavily on all aspects of organic chemistry and chemistry that we've done before. So let's do the observations and retrosynthesis. Remember we said that retrosynthesis here really means working backwards. So we start with the product, target molecule, make some observations, and see how we can put the functional groups together. The first observation is we have an OH, an alcohol. And we know from past experience that alcohols are made from the hydration, addition reaction of water across double bonds. So if we had here a double bond, we can add water in an anti-Markovnikov sense. So now we're introducing terms that you may have forgotten, which means you have to go back and refresh your memory with the reactions that we did last semester. As an anti-Markovnikov addition to a carbon-carbon double bond to give an alcohol. Notice this one, the reactant now we can look at, it has bromine, which is a leaving group. So we can easily make here an alkene. So we know we need to make the alkene right here. Right here. So we have to make a careful selection here in the type base for that elimination reaction. So you can see here we are applying the concepts that we have learned to solving a synthesis problem. Let us see what is a potential answer. Potential answer here would be LDA, elimination reaction, to give here the Hoffman product, or the least substituted alkene. Then to get OH and H added to that double bond, we need an anti-Markovnikov addition. You may recall from last semester, one way of doing an anti-Markovnikov addition is to use borane and hydrogen peroxide. 2 steps. Notice 2-step reaction here. So this would be the synthetic route that you could use to carry out that reaction. Let us look at a last slide here before we end this lecture here. So, as you can imagine, if you have a leaving group here, here's a leaving group, the trimethyl ammonium ion. As you can see, that is a pretty large leaving group. Why is it a leaving group? Because after it has left, and I'll put the 2 electrons here that it's taken from this bond, this is a very stable conjugate base, trimethylamine, stable base, which means that this is a good leaving group. But it is a bulky leaving group. So in this case, if you use a small base, because it is a bulky leaving group, it will abstract this hydrogen and not this one. Just too crowded, because we have 2 R groups here already and this bulky leaving group. It will abstract this proton here, hydrogen as a proton, to put the double bond here, and that product is called the Hofmann product, and we'll see later on that reaction is called the Hofmann elimination. So again, you should be able to combine these concepts to solve different problems. I think this is our last slide, and yes, it is. So again, this is our first lecture for the semester. So please use these slides and video lecture as supplemental material for reading the book. So you'll have to read the book and solve the problems, and of course I'll give you a tutorial set this weekend. Make sure you start working these, solving them, and of course to solve these problems, it's basically the applications of the concepts that we've learned. So you got to really think carefully and apply that understanding to solving problems. Okay, I will post another lecture video shortly on, well, before too long, on this chapter. But take your time and read this, and I will provide more information before the weekend on next week, if we'll have a quiz or starting the following week. So stay tuned. So once again, continue to study hard. All the best for the semester. Start it with a running start, so you'll keep that momentum going. So continue to study hard and look out for the next video. Okay? Bye.